So I'm going to talk about multi-level modeling, and this is kind of, I guess, a subject that I have been doing since I became an academic and before as well. So a bit about my history. I did my undergraduate and PhD at the University of Bristol, and Bristol is the home of the Centre of Multi-Level Modelling, which goes back a good 40 years now. And the people that worked at Bristol that used to work at the Institute of Education in London are among the people that first developed these models, starting in the 80s, but they've been continuously developed ever since. And really what they're about is doing something about the problems with this model. So hopefully, or possibly, this is familiar with people. It's a very simple regression model. Does everyone know about what regression is? And seeing some nods. If you don't worry too much. We've got an x variable, which we're saying in some way is related to a y variable. We've got some dots as a result of a scatter plot, and we fitted a line of best fit through it. Okay? And this line of best fit can be defined by two things, right? It can be defined by the intercept, that is the value of the expected value of y, when x is 0, and the slope, that is how steep this line is. So for each unit of x across, how much does y go up? And those two numbers are often called beta 0 and beta 1, so they can be put into this equation. And this equation, if you've done GCSE maths, this is y equals mx plus c. Okay. Interestingly, in different countries they use different letters for that. I don't know why. So in some countries it's y equals mx plus b, I think. Sometimes it's not m. But anyway, in general, or at least often in social science, we use beta 0 and beta 1 for some reason, just because normal letters are too easy, and we like to keep statistics as uninclusive as possible, apparently. But you can use whatever. You can use beta, m, and c. You can use fluffy cloud and cute cat if you want. I don't really care. These are just going to be numbers which tell you how high up this line is and how steep it is. And that's fine. This model is okay, but there are some issues with this model, because actually when we're running these models, we're making some assumptions. And one of the assumptions that we're making is that the residuals, so that's the stuff that we don't know about, right? So the stuff, the reason why this point is higher than the line. So let's imagine this is house prices or something, and this is number of rooms in the house. Okay, so in general, if you've got more rooms in your house costs more. Maybe that house has a nice bathroom. Maybe this house that has a not nice bathroom, tiny garden. That one's got a garage. That one's, I don't know, next door to some criminals and some drug dealers, something like that. That means that these are kind of stuff that we don't know about, right? We've got a big data set. We can't measure all of these things. There's all sorts of stuff we don't understand, which might include the person that bought it last was a bit stupid and paid too much, right? All this stuff, all this random stuff we don't know about, we're kind of chucking into that E term. Now, often when we talk about regression, often you will be been taught, or there are some assumptions about this number. They're probably wrong, but let's not think about it too much, because if we think about it too much, we have to admit that there's some problems here, and so let's just not talk about that too much. Not only are we not going to talk about the assumptions, but actually we're not going to talk about those residuals at all. We're going to forget about them, and all we're going to talk about is that line. Okay, that's kind of how statistics courses often go. But actually, those assumptions matter, firstly. So from a technical point of view, that's important. It kind of matters if those assumptions are correct. And one of those assumptions is that these data points are independent from each other. That is, that this model has accounted for all the systematic stuff, all the stuff that is really kind of matters, all the stuff that we really want to know about, and that only kind of random right noise remains. And that's just not realistic. We know that that's not the case, but we kind of have to make this assumption. But the other problem with this is that actually, by ignoring this E, we're forgetting about all of the stuff, all of those interesting factors that are different from each other. And we have to do that to some extent. We've got a big data set, and each data point has different reasons for being there. That's why we're doing this modeling, right? A model, when people talk about a model, it's exactly the same as any other model, right? So a model village is an example of a model, right? It's kind of like the village, but it's a bit smaller and a bit simpler and a bit easier to kind of see as a whole. It's exactly the same with a model. We're trying to simplify things to be kind of understandable to ourselves. And that means losing some information, but we don't want to lose everything. And it turns out that once you know these hierarchies exist, or these kind of structures in society exist, you see them anywhere. So let's imagine that I had this brilliant theory that people with blonde hair perform better in exams. Okay? So what I do is I create a data set of all of you, I record all of your hair color, I record your exams, and I run my regression, and I'm a bit annoyed because I don't find a result, right? Damn, my theory seems maybe it wasn't right. And then I have this bright idea that instead of collecting one hair from each of your heads, I'm going to take 100 from each of your heads. I'm going to have a much bigger data set. I've got a huge amount more data now, 100 times I had before, and I've run my regression, and now I've got a significant result. Okay? But of course I don't really have a significant result, right? What I've actually done is just replicated my data 100 times. But what that I have as a result is a multi-level data set where I have hairs nested on people's heads. And these structures exist everywhere. So students exist in schools. That is, students that live in the same school are to some extent similar to the students that are also in the school. That might be because of catchment area, might be because they've got to know each other, right? They talk to each other. Voters are nested in electoral wards. They're kind of similar to each other. Just like the hairs on your heads are similar to each other in terms of how they affect your exam results, voters in electoral wards are similar as well. These models have been used in all sorts of areas, used in veterinary science, cows nested in farms. Cows in the same field are more similar to each other than cows in a different field, and so on. So those are kind of hierarchical structures where all of your hairs are in the same head, all of the students are in the same school. You can have non-hierarchical structures as well. For instance, individuals can be affected by more than one context. They're affected by their school, but they're also affected by where they live. And people in one school don't all live in the same place, or vice versa. So what we're going to do in this with a multi-level model is we're going to make things a bit more complicated. So let's imagine there are two places, okay, where these house prices exist, the red neighborhood and the yellow neighborhood. What we're going to do is take that error, that E term, I don't like the term error, call it a residual, because error implies it's wrong. It's not necessarily wrong. We're going to take that error and that residual and we're going to divide it into two. So we're going to have one bit which is telling us about differences between neighborhoods, and another bit which is telling us about differences within neighborhoods. So you can see we have the yellow neighborhood and it's got its own line, which is much like this line, but it's been made a bit lower because it has a lower value of this neighborhood residual. And the red neighborhood has a higher value of that U value. And then you've got data points around them. So this neighborhood, this house is a cheap house in a cheap neighborhood. This neighborhood, this house, it turns out, is actually quite expensive for the neighborhood, but it's actually cheap compared to the overall line of the overall world. So what are we doing when we do this? Well, firstly, we're modeling complex structures. So rather than just assuming that the world is flat or that the world has no variation, saying that actually there are structures in data sets, structures in the world like the ones that we've talked about. Secondly, we're talking about heterogeneity and we're talking about difference. What does that mean? Well, it's saying that actually, so people often say that statistics is about mean variance, right? So it's about finding the average and then finding how much it varies around it. That's what you get taught in the first week of your intro statistics class. And then everyone forgets about the variance bit. Everyone forgets that everyone's different and they're only interested in the average line, right? What we're saying is that actually often that heterogeneity is just as interesting as the average line. And we actually want to look into it, we want to model it, we want to understand it. Another way of thinking about that is dependency. That is, individuals that are in the same neighborhood or in the same school are dependent on each other statistically in some way. That is, and that might be literally that this student borrowed this student's homework, right? They might actually be related, and later on Griff is going to talk about network analysis to try and get even closer to that. But in some way, these individuals are dependent on where they are and on kind of the similarities to each other. And finally, we're interested in context. So we're interested in how these higher level units, how these schools, how these neighborhoods affect individuals. So if you're in, your house is in this neighborhood, what is it about this neighborhood that makes it more particularly expensive? Maybe there's a park nearby, or lower pollution levels, or something else, maybe low crime rate, lower deprivation, and so on. We can think about not just how the individual house, the fact that it has a nice bathroom or a garage or a small garden, those things all matter, but as well as that, we can look at how context matters, how the neighborhood, living on a particular street or a particular neighborhood, can have an effect. So we can get these two levels, and potentially more levels if we want, that tell us more about this. Not only that, but actually we can find the incorrect answer if we don't do this. So here is some made-up data. We want to know what the relationship between x and y is. If we run a single several regression model, we find that there's a negative relationship between these two. If we run a multi-level model, we find that there's actually a positive relationship between these two. We find literally the opposite answer. The reason we find this is because actually there are different effects within and between these groups. That is, there's kind of a negative correlation between the groups, which is causing this negative effect. But actually, within individuals or within these groups, there's a positive effect. Which is correct? Is it a negative effect? Is it a positive effect? Well, it's potentially both. So both of these have an effect. But if we just do this, we can't find out that, right? We found a completely kind of messed up version of what's going on. We really need to split these into levels to find out what is going on in this relationship. So some examples. So one example of this is a thing called school league tables. So they've actually changed the system in recent years to another measure. But it used to be the case that these school league tables were done on the basis of a multi-level model. So what are called value-added league tables basically was a plot of your attainment in your GCSEs against your attainment when you arrive at secondary school at age 11. Okay? So really what we're saying here, well, firstly, if you do well at age 11, you probably do well later on. But also there are some differences between schools where this blue school perhaps is particularly good, this grey school is particularly less good. So that's basically what school league tables are, right? They're a ranking of these schools. But that's potentially problematic because it might be that the truth is actually this. Okay, so this is, you can also do with multi-level models. It's called a random slopes model because the slopes are different. We're allowing the slopes to be different. And this now tells quite an interesting and slightly different story, right? That's much harder to put in a league table. That is, the blue school is pretty good. Oh, that's interesting. You can't see the blue school on the graph. There's a blue line. Oh, no, there's not. The blue line is just coming out grey. That grey line at the top is what I mean when I say blue. So that looks like it's the best school if you're doing well at age 11. But if you're not doing well at age 11, there might be a different school that's better for you. And this has quite interesting policy implications around school choice and things like that. Because, of course, if you ask parents, where do you want to send your kids to, here is more information, they all think their kids are up here, right? Everyone thinks that their kids are really good, that even if they're not doing well in their exams, it's probably the teacher's fault, and so on. So actually, in terms of, this presents some difficult questions in terms of choice and things like that, but it allows us to see a much more interesting, broader question in terms of social science, right? We can see the fact that schools seem to matter more for this high-end student, the top students, it matters more. There's a bigger gap there between these two lines than there is down here. If you're a low-performing student, it's not that much that any school maybe can do for you. There are problems earlier on, perhaps, which in itself is an important policy point. If you want to invest in education, do it in the early years, because actually, once you get to age 11, it's kind of too late by then. Here's another example, also a bit depressing, I'm afraid, sorry about that. So this is an example from a while ago, 10 years ago now, this paper was released. And this paper had a huge policy effect, right? This was a paper called Growth in the Time of Debt by Reinhardt and Rogoff. And this basically showed that for countries that had lots of debt, the country has a lot of debt, their growth was lower. Okay, including to the point of being negative growth for some countries. This was picked up by a lot of right-wing politicians, Paul Ryan in the States, David Cameron here, as a reason for implementing austerity politics. Okay, so the reasons for implementing austerity politics were, we have a big national debt and that's harming our economy. We need to bring the debt down. We need to bring the deficit down. So the conclusions of this paper were used to implement huge cuts in the UK. Barack Obama to some extent resisted it in America, but not completely. Turns out that there were some problems with it. The main one was that they'd used an Excel spreadsheet to do this, and they'd accidentally deleted all the countries whose names began with A to F, which led to some errors, unsurprisingly. Actually, more important than that, there were some other exclusions and some other weird weighting systems, which meant that actually these results were more extreme than they should have been. But actually, they still showed a negative effect to the relationship between growth and debt. This, by the way, made quite a splash in the news because it was found, these errors were found by a graduate student who had been given an assignment to replicate a paper. He tried to replicate the paper and he couldn't. Called the authors, asked them why, tried again. Asked them for their code, they said no, kept trying. Eventually he realized this was the problem. If you want to get a job, write a paper like this. This is this is a way to make sure you get hired after you've graduated. He's now an assistant professor somewhere in the States. But even with his results, he found a negative relationship between growth and debt. So a paper that I wrote a few years ago asked, well, actually, why should this effect be the same everywhere? Why should this be the same in all countries everywhere in the world? Why should it be the same in the UK compared to the United States, compared to Japan, where all these countries have quite different economic systems and so on? So we ran a multi-level model on this, which resulted in a graph that looked like this, where it's kind of a mess, right? So in some countries, there is this negative effect. But in other countries, there's a positive relationship. So I think that's Norway. There's a positive relationship between growth and debt. And in the UK, there's no relationship at all. So all of those kind of policy decisions made by David Cameron on the basis of these, kind of models, of these kind of science, were actually somewhat dubious. So I said earlier, last example. I said earlier that in statistics it's about mean and variance, and that often people forget about variance. Multi-level models really give you an opportunity not just to think about variance in itself, but also to explicitly model it and model how it varies. So variance can be different for different groups of people. Okay? How spread out people are can depend on whether they're poor or rich, or whether they're well educated or not, or whatever else. And we saw that here, right? We saw that actually schools, there's more variance among schools for high-performing students compared to low-performing students. And we can plot these and find these in what's called variance functions, which allow us to find not just the variance that happens. So before, when we ran a single-level regression, we did estimate a variance. There's just one variance, which was how spread out those dots are around the line. Now we can estimate not just variances at different levels, so the variance of schools and the variance of pupils, but also we can allow those to be different for different sorts of pupils. As an example of this, just because it's a bit weird, I did a paper that came from an undergraduate dissertation on Formula One driving, where we looked at where the variance in Formula One race results came from. So I don't know, are there any Formula One fans in the room? God, there's none. That's a nightmare. No, it's fine. In Formula One, it's a slightly weird sport because there's both an individual race and a constructor race. Okay, so individuals are racing against each other, but also they race for a team, and that team, there's also a kind of team league as well. And so a key question amongst Formula One fans that they argue about in the pub is how much the driver really matters. Okay, is it actually mainly down to which team they race for, or does the driver make a difference? And so we answered that question using variance functions, because really how much drivers matter, the question really can be asked as how much variation is there in drivers and in teams, and how much has that changed in this case over time. And we can see this is the team variance, this is the driver variance, don't worry about the middle one for the moment. You can see the team variance is much higher and also is increasing. So as technology improves in the sport, actually which team you race for has become more important than the driver. We were also able to make a league table of the greatest Formula One drivers of all time, mainly because it really annoys fans. So it's a kind of study that was really, because often when you study you're worried it's going to get picked up in the press and they're going to misinterpret it and cause problematic policy. With this I didn't really care if they misinterpreted it. I quite enjoyed the arguments that happened on the Daily Mail boards as a result. If you're interested, we found Juan Manuel Fangio, the greatest driver of all time. He raced in the 50s. You can see some drivers that are more recent. Lewis Hamilton is up there. This was a few years ago. It wouldn't surprise me if Lewis Hamilton had moved across now, since he's won pretty much everything since then. So overall, what these models are doing are kind of two things, right? So firstly, they're technically better, right? Those assumptions that you made in your single level model, you now don't have to make such strong assumptions, which is good. But more importantly for me, they allow me to answer more interesting questions. Okay? They ask me to understand questions about difference, questions about heterogeneity, about why there is spread, why there is difference in one group of people but not another. And these are widely applicable to a range of different questions and subjects. So, one-day course, that's going to happen on the 22nd of May. Like all the other courses that we run, it's going to be a mixture of lecture-y type things and practical exercises. That's going to be an ML win, and there's going to be no expectation of software for that, so don't worry about that if you never use the software. Even if you decide not to go to that, it's worth pointing you to some quite useful resources. So the Centre for Multilevel at Bristol have a huge load of resources on their website, which include some online courses which start with simple stuff. So if you want to remind yourself about multiple regression, you can go through those online courses there, going on to multi-level models, to even more complicated stuff using different dependent variables and things like that. And it's all completely free. You need to give them your details so that they can steal your identity at some point, but you don't have to pay anything, apart from, I guess, your identity, potentially. And that's pretty much it. I talked about some of my work, and that's because I'm a shameless narcissist, those are some of the papers. If you want to know anything more, it's lunchtime now, so you can ask me then. Well, ask me now, firstly, but also that's my online details.